Ever imagine a place where time itself takes a break, gravity reigns supreme, and not even light can make a getaway?
Yeah,
That, my friend, is the captivating realm of black holes, and today we're diving headfirst into their mysteries.
absolutely. And we've got a treasure trove of resources to guide our exploration, from the latest NASA findings to Brian Cox's mind-blowing insights,
Well,
and even some illuminating explanations from PBS Spacetime.
buckle up, because this deep dive is going to take you on a wild ride through warp space-time and mind-bending
Yeah,
physics.
absolutely.
Let's start with the basics, or at least as basic as things can get when you're talking about objects so dense they defy our everyday understanding of reality.
Right.
When we say black hole, we're not talking about some empty void in space.
Precisely.
Yeah.
Okay. It's not a hole in the traditional sense, but rather a region where gravity is so incredibly intense that nothing,
Nothing.
not even light, the fastest thing in the universe, can escape its clutches.
Wow.
Imagine taking an object as massive as our sun and squeezing it down to a size smaller than a city.
Wow, squeezing the sun to something smaller than a city.
That's the kind of extreme density we're talking
What's
there.
it almost impossible to wrap your head around?
Yeah.
It's no wonder these things can warp space-time like a bowling ball on a trampoline.
And it's that warping of space-time that leads to one of the most defining features of a black hole, the event horizon.
Event horizon, okay.
This isn't a physical boundary like a surface you could touch, but rather a point of no return.
Call point of no return.
Cross the event horizon and you're on a one-way trip to the singularity at the heart of the black hole.
So once you cross that invisible line, there's no turning back.
That's right.
No matter how powerful your spaceship engines might be.
Exactly.
It's like falling off a cosmic waterfall.
Yeah,
Once you're over the edge, gravity has you in its grip.
that's a great analogy.
But here's a question that's been bugging me. If black holes are, well, black, and they don't emit any light, how in the universe do we even know they exist? It's not like we can just point a telescope at them and say, aha, there's one.
You're right. Finding black holes is like searching for a cosmic needle in a haystack, but instead of a needle, it's an invisible object that devours light itself.
Okay.
We have to get creative and rely on their effects on their surrounding.
Okay, so it's like detective work on a cosmic scale. We're looking for clues, for telltale signs that betray the presence of these hidden behemoths. So what kind of clues are we talking about? How do we catch a black hole red-handed, so to speak?
One way is to look for the after effects of their cosmic feasts.
Cosmic feasts, okay.
As matter spirals into a black hole, it doesn't go quietly. Instead, it heats up to millions of degrees, emitting a torrent of X-rays.
Oh, wow.
These brilliant displays of high-energy radiation act like beacons, signaling the presence of a feeding black hole.
So it's like the black hole is having a cosmic barbecue, and we're seeing the glow of the grill, even if we can't see the grill master itself.
Exactly. And sometimes these cosmic barbecues get really wild.
Wow.
We're talking quasars, objects that shine brighter than entire galaxies combined.
Wow.
Imagine a single black hole outshining hundreds of billions of stars.
Oh, my God.
And it's all powered by matter spiraling into its depths, releasing incredible amounts of energy in the process.
Quasars are like the universe's ultimate light shows, powered by the most extreme objects we know of. It's mind-blowing to think that something we can't see directly can have such a profound impact on the universe around it.
It really is.
And speaking of seeing the unseen, I've also heard that we can detect black holes by watching how they make stars dance.
Oh, absolutely.
Is there any truth to that?
Absolutely.
Okay.
Imagine a cosmic ballet with a supermassive black hole at the center. Its immense gravity dictating the movements of stars orbiting around it at incredible speeds.
Wow.
By studying these stellar orbits, astronomers were able to confirm the existence of Sagittarius A, the supermassive black hole lurking at the heart of our very own Milky Way galaxy.
Wow, so there's a black hole at the center of our galaxy.
There is a supermassive one.
It's like watching a cosmic waltz, but instead of dancers, it's stars swirling around an invisible partner. And that discovery was a pretty big deal, right?
It was a landmark achievement in astronomy, earning the scientists involved the Nobel Prize in Physics in 2020.
Yeah.
And it's a testament to the power of observation and deduction. We can uncover the secrets of the universe even when we can't directly see what we're looking for.
Talk about a cosmic mystery solved. It makes you realize how much we still don't know about the universe, but also how much we can learn by paying close attention to the clues it gives us.
Absolutely.
And sometimes those clues come in the form of ripples in the very fabric of space-time itself.
That's right.
We're talking about gravitational waves,
Yeah.
a prediction of Einstein's general relativity that was finally confirmed in 2015.
Amazing, isn't it?
Gravitational waves. Okay, you're going to have to break that one down for me.
Okay.
What are they and how do they help us find black holes?
Imagine a pebble being dropped into a pond, but instead of a tiny pond, it's the vast expanse of space-time.
Okay.
And the pebble is a cataclysmic event, like two black holes colliding.
Wow.
The ripples from that collision, those are gravitational waves.
So we're talking about literal ripples in the fabric of reality.
Yeah.
That's wild.
It's mind-boggling.
But how do we even detect something like that? It's not like we could just dip our toes in space-time and feel for a wave, right?
It's even more mind-boggling than that. We've built these incredibly sensitive instruments here on Earth, giant laser interferometers
Wow.
that can actually measure the infinitesimal stretching and squeezing of space-time caused by these passing waves. It's like listening to the universe whisper its secrets. Secrets that black holes, with their extreme gravity, happen to be particularly good at telling.
It's like we've built cosmic ears that can pick up the faintest echoes of these cataclysmic events happening billions of light years away.
That's a great way to put it.
That's absolutely incredible.
Yeah.
And I'm guessing those aren't the only tricks up our sleeves when it comes to finding these invisible enigmas.
You're right, there's another fascinating phenomenon called gravitational lensing.
Gravitational lensing.
It's like black holes have a knack for making the universe itself act like a giant magnifying glass.
Okay, now you're just messing with me, right?
No, not at all.
How can something invisible act like a magnifying glass?
I know, it sounds like something straight out of Alice in Wonderland.
It really does.
But it all comes down to the way massive objects warp space-time around them.
Okay.
Imagine a black hole sitting between Earth and a distant galaxy.
Right.
As light from that galaxy passes by the black hole, its path gets bent by the warped space-time.
Okay.
And that bending can distort and magnify the light in a way that we can detect.
So we're not seeing the black hole directly, but we're seeing its effect on the light passing by it.
Exactly.
It's like a cosmic shadow puppet show, where the black hole is the unseen puppeteer distorting the light to reveal its presence.
That's a great analogy.
That's seriously cool.
Yeah.
But, all this talk about black holes bending light and warping space-time, it kind of makes you wonder, are these things really just cosmic vacuum cleaners sucking up everything in their path? Or is there more to the story?
That's a question a lot of people have, and it's understandable why they might think that.
Right.
But the truth is, black holes are a bit more nuanced than their cosmic vacuum cleaner reputation might suggest.
Okay, I'm all ears. Let's bust some black hole myths.
Yeah.
What's the real story here?
While their gravity is undeniably powerful, it's not some kind of infinite force that sucks up everything in the universe.
Okay.
In fact, from a distance, a black hole's gravity acts just like the gravity of any other object with the same mass.
So if we could magically replace the sun with a black hole of the same mass, Earth would just keep on orbiting like nothing happened.
Exactly. We'd be in for a world of darkness and cold.
Right.
But our orbit wouldn't change a bit.
Wow.
It's only when you get up close and personal, really close, that a black hole's extreme gravity starts to flex its muscles. Think of it more like a cosmic strongman, incredibly powerful up close, but its influence diminishes with distance, just like any other force in the universe.
Okay, that makes a lot more sense. It's like standing near a bonfire. You definitely feel the heat when you're right next to it, but
Right.
step back a few feet and it's much more manageable.
Exactly.
It's all about perspective.
It is.
But speaking of getting up close and personal with black holes, let's talk about one of the most terrifying concepts in astrophysics, spaghettification. Even the word itself is enough to send shivers down your spine.
Yeah, it's not a pleasant thought.
It's definitely not a fate I'd wish on anyone.
Yeah.
Imagine this. You're falling feet first towards a black hole.
Okay.
As you get closer, the difference in gravity between your head and your feet becomes more and more extreme.
Right.
Wait, hold on. You're telling me the gravity at my feet would be stronger than the gravity at my head.
It would.
How is that even possible?
It all comes down to the way gravity works.
Okay.
It's not a uniform force that acts the same everywhere.
Right.
The closer you are to a massive object, the stronger the gravitational pull.
Right.
So as you fall towards a black hole, the gravitational force acting on your feet, being closer to the black hole, becomes significantly stronger than the force acting on your head.
Okay, I think I'm starting to get it.
Okay.
So what happens next? I'm guessing it's not pretty.
Not pretty at all. This difference in gravitational pull, known as a tidal force, starts to stretch your body and stretch
Hey.
and stretch.
Like a piece of cosmic chewing gum.
basically.
Ouch. I can already feel the chiropractic bills piling up. But on a serious note, that's terrifying and fascinating at the same time.
It is.
It shows how powerful these tidal forces are near a black hole.
Yeah.
It's not just about the intense gravity, but the difference in gravity's pull across even relatively small distances.
Precisely.
And these tidal forces are why black holes are often depicted as these cosmic whirlpools.
That's right.
As matter gets pulled in, it spirals around the black hole, forming a disk of superheated material called the accretion disk.
Exactly.
We talked about it earlier when discussing quasars. The
Yeah.
accretion disk.
Yeah.
It's like the ultimate cosmic demolition derby out there.
It is quite a sight to imagine.
All that matter, spinning and colliding at incredible speeds, must generate an unbelievable amount of energy.
Oh, absolutely.
But I thought nothing could escape a black hole once it crossed the event horizon.
Right?
How can there be these giant jets of energy shooting out?
That's a great question.
It's like trying to stop a runaway train. How can anything, even light itself, escape that kind of gravitational pull?
It's one of the most intriguing questions in astrophysics.
Yeah.
What we've come to realize is that black holes are far more dynamic than we initially thought. They're not just passive objects that sit there and gobble up matter. They're actively shaping their surroundings through these incredible jets of energy and particles.
Okay, now I'm really interested. How do these jets work? What are they made of?
Okay.
And how can something escape the clutches of a black hole after it's supposedly trapped forever?
The key to understanding these jets lies in the complex interplay between gravity, magnetic fields, and the accretion disk itself. You see, the accretion disk isn't just a chaotic jumble of matter. It's also threaded with powerful magnetic fields generated by the swirling charged particles within the disk.
And we're back for more of this deep dive into the mysterious world of black holes. We've gone from the point of no return to the unbelievable brightness of quasars, but something tells me we're only just scratching the surface of these cosmic enigmas.
It's true. Black holes are like cosmic puzzles.
Yeah.
Each discovery leads to more questions and pushes the boundaries of what we thought we knew about the universe.
Well, I'm definitely feeling puzzled after our last segment. We were talking about those powerful jets of energy and particles that seem to defy a black hole's immense gravity. You're about to explain how those jets form. It sounded like some seriously cool astrophysics.
Yeah, it all goes back to the accretion disk, that swirling vortex of matter spiraling around the black hole. Think of it like this. As matter falls inward, it's not a smooth, orderly process. It's more like a cosmic traffic jam.
Okay.
With particles colliding and rubbing against each other at incredible speeds.
Okay, so you get friction, heat, and a whole lot of chaos. Sounds like a recipe for some pretty intense energy.
Exactly. And it's this intense energy combined with the incredible rotational forces near a black hole that causes these magnetic fields to become twisted and amplified, forming what we call magnetic fields.
Magnetic fields, and now we're getting to the good stuff. How do these magnetic fields turn a black hole into a cosmic cannon, shooting out jets of energy across millions of light years?
Imagine these magnetic field lines as a series of tightly wound springs coiling around the black hole. As matter gets sucked in and whipped around by the black hole's rotation, these magnetic springs get twisted tighter and tighter, storing up incredible amounts of energy.
So it's like a cosmic slingshot, pulling back further and further
Until, snap. Some of that pent-up energy has to go somewhere, and that's where the jets come in. These magnetic fields act like a release valve, channeling some of the superheated matter and energy away from the black hole's equator and focusing it into these incredibly narrow beams.
So instead of falling into the black hole, some of that matter gets a one-way ticket out of the galaxy, launched into space at nearly the speed of light.
That's the general idea. Though the specifics are still a hot topic of research, we're talking about some of the most extreme environments in the universe where our current understanding of physics gets pushed to its limits.
Well, it's certainly a reminder that the universe loves to keep us guessing. But speaking of mind-bending physics, we've touched on this briefly before, but I think it's time we revisit it. Hawking radiation. This idea that black holes aren't completely black after all has always blown my mind. How can something that's supposed to trap everything, even light, actually leak energy back into the universe?
It's one of Stephen Hawking's most profound contributions to physics. And it all comes down to the weird and wonderful world of quantum mechanics.
Quantum mechanics, the realm of the very, very small, where particles can be in multiple places at once and cats can be both alive and dead.
Exactly. At the quantum level, the universe is a much stranger place than our everyday experience suggests. And even at the edge of a black hole, at that point of no return we call the event horizon, quantum weirdness still holds sway.
Okay, so how does quantum weirdness make a black hole leak energy?
It involves something called virtual particles,
Okay.
which are constantly popping in and out of existence throughout spacetime, even in the vacuum of space. Think of them as particle pairs. A particle and its antiparticle that borrow energy from the vacuum exist for a fleeting moment and then annihilate each other, returning the borrowed energy.
So these virtual particles are like subatomic borrowers, constantly taking out and repaying energy loans from the universe.
You could think of it that way. Now imagine a pair of these virtual particles popping into existence near the event horizon of a black hole. Sometimes one particle might fall across the event horizon while the other manages to escape.
So it's like one particle gets swallowed up by the black hole while the other one gets flung out into space.
That's the gist of it. And here's where it gets really interesting. That escaping particle carries away with it a tiny bit of the black hole's energy, reducing its mass ever so slightly.
So over vast stretches of time, these escaping particles slowly chip away at the black hole's mass, causing it to evaporate.
That's the idea, though it's an incredibly slow process, especially for supermassive black holes.
Right.
We're talking about timescales far, far longer than the current age of the universe.
So in a way, even these seemingly invincible objects aren't eternal.
It seems so. Even black holes have a finite lifespan, though it's a lifespan that dwarfs everything else we know in the cosmos.
It makes you wonder, if black holes can evaporate, what happens to all the information they swallowed? Does it just vanish, or does it escape somehow?
That, my friend, is the heart of the black hole information paradox, one of the most profound, unsolved mysteries in physics. And there are no easy answers.
It's like the universe likes to keep its biggest secrets locked away behind event horizons. But that's part of what makes studying black holes so captivating. They challenge our assumptions, push the limits of our understanding, and force us to confront the vast unknown that still surrounds us.
Precisely. And as we delve deeper into the mysteries of black holes, we're not just learning about these extreme objects, we're gaining a deeper understanding of the universe itself, its fundamental laws, and perhaps even our own place within its grand cosmic tapestry.
Well said. It's been another incredible deep dive, and as always, thanks for joining us on this journey to the edge of the unknown. Until next time, keep looking up at the stars and pondering the infinite wonders they hold.